Hello everyone, in this video we'll see on friction stir welding simulation or friction stir welding analysis using this Abaqus environment. So we determine the nodal temperature or estimate the temperature contour along the workpiece joint line and also other parameters like one mistress or any other parameters you can determine. It's up to you. But I will show you how to perform this friction stir welding process on this Abaqus software. So this is video important for you in your research or any finite element understanding on this friction stir welding under Abaqus environment. So let's see some highlights about how friction stir welding is. So friction stir welding means what you call it, a type of welding process when applying a friction or a pressure on workpiece so that this workpiece will soften due to the frictional heat. So this is what you call it tool. This tool will rotate on top of this workpiece. This pin, the so-called probe, will move down or penetrate the workpiece between two mating parts, so it will steer a material from one advancing side to retreating side, so that joining or attachment will take place. So in this process, what we are going to see is simulate or animate like this on this Abaqus software. So in reality, the spindle and this shoulder will rub on the workpiece so that heat will generate due to friction. So that frictional heat is enough to soften the material and welding will takes place before the melting or the melting of the that's why we say this solid state welding process. So we'll see like this how the temperature profile along or across the width of the workpiece. When the tool moves from one end to the other end, the temperature profile looks like this. So we'll plot the graph in Abaqus post-process step, time there and temperature. So through time how the nodal temperature will change. As you see from the graph, for example, you see at the time it will elevate, the temperature will highly elevate at some point. Then after, when the welding tool pass, it will cooling down, and at the end it will have the temperature equals to environmental or room temperature. So let's begin this step by modeling the workpiece as well as the welding tool. Anyway, what's the beginning step is to model a 3D model for workpiece as well as this welding tool. In addition to that, we'll make three parts. One is Eulerian and the other Lagrangian. As well as rigid body, we treat as a rigid body this tool because we concentrate on the temperature on workpiece, not for a tool at this time. So let's begin this. Let's start workpiece or Eulerian 3D deformable and select in this type Eulerian extrude part. You can leave approximate size as a default 200. Then put a rectangular part with a definite thickness. Let's put 7 and this dimension 40. And extrude depth extrusion depth, you can put 70. This part is Eulerian. Then other Lagrangian workpiece part, then 3D deformable solid extrusion. Put the same procedure. .40 is okay. In dimension, I put 3. .70. Then tool, welding tool, 3D deformable solid. Here in type we select revolution part, so put like this. Any dimension later on will give the dimension for these lines. .5 is enough. Let's say 2.5. And reduce this dimension about 4 is enough. So let's put some fillet on this corner. Select this fillet, put 0.25 between these two lines. .5 on this corner and at the end. Any dimension you can put as per your need. So this we have done parts. Parameters revolution with 360 degree. Put like this is a welding tool. Then go to property, create a property aluminum alloy. Give density 2.7 E-09 kilogram per millimeter cube. So keep in dimension consistency in this Abaqus software. Is most important parameter is the dimension you give in all parameters must be consistent. So we have given a temperature in Kelvin or degree C, whatever you can put, but in dimension we have given millimeter, so we must give the mass density or density of the material per kilogram per millimeter cube. So other elastic, modulus of elasticity, we see 17,000 in Poison's ratio 0.33. So here plastic. In plastic we select Johnson-Cook material model. And here in sub option we rate dependent and put here 0.011 and exponent 1. Sorry, here is Johnson-Cook and see 0.011, then 0.1. In thermal conductivity, because we are going to do on temperature dependent material, so you must put, don't forget this part, conductivity, thermal conductivity of a material, put this much watt per meter per Kelvin. In specific heat, $67,000, and then expansion we put 2.35 E minus the power 5. Okay, this is all about aluminum property. Then tool property, tool material property will put from this we have given here, tool, or we can say the metal is steel, so put the density 7.8 minus 0.9. Elastic, he put 210,000, input poisonous ratio 0.29. Other part is specific heat. Thermal conductivity, put exit and then specific heat. Okay, then go to assemble, create an instance and assemble properly all 3 parts. Translate one part, select the part. Okay, then a point, which point move to other destination, so select this point and select the next point, so these 2 points will coincide together. So assemble like this. Again select translator, select translate instance, select a part, then select a point where you move like this. Okay, the same procedure, do the same for this tool. Select, okay, okay, welding tools, assemble like this. Other part we want to create a partition for a workpiece. Select 3 point, click on all these 3 pointers on the same plane, create partition. Okay, done. So go to the Eulerian part, do the same procedure, select 3 points and select 3 points which are located on same plane, create part. Okay, so assemble like this. So other step, go to step, select in procedure general and dynamic temperature displacement explicit type. So in first step there is what to call it, plunging procedure. The tool moves down okay, then put time period, appropriate time period 3, and this, then go to dueling the same project dynamic temperature displacement explicit, then put dueling for this much time. Dueling means rotate at the same position without translation, no translation movement is there, but dueling is it up to the material soften enough, tool will rotate at one stationary position. That is what you call it, dueling process. Other is welding, the third step, welding is there. Welding, this welding tool will move translation in longitudinal direction as well as it rotates. Rotation and translation movement is there. So in this process the material will begin joining together. So this dueling process. Then in this step module we select this what call it field output request manager and edit it. You can select any parameters what you are going to analyze, or your main target you can select from this. By default so many parameters are selected here, but you can remove and also add. It's up to you. For example, our main target is to determine the temperature profile or temperature change along the workpiece. So here nodal temperature must be checked here, and also other parameters, maybe elemental temperature also may check, other reaction flux, and any parameters you can select. In failure, for example, failure and fracture, if you need tensile damage or compressive damage, you can select this, up to you. Okay.